for any of you that don't know, Sentinel have been developing best practice water treatment for around 25 years. We're a UK-based company incorporating chemicals for heating and chilled water systems, as well as a few physical devices to manage scale in hard water areas. Across the CPD, we'll look at reasons and highlight why corrosion and lime scale occurs, the problems it can create, and what you can do to help prevent these problems. As we said there, so the section 1 will cover why it's so critical and a few of the industry guidelines. Just as a point of note, a topical little joke, the school closure has got nothing to do with the current pandemic. It's to do with asset depreciation. So why is water treatment so critical? You'll see there in the bottom right image, it's a 2.5-inch pipe of untreated scale issues. As a result of the scale being untreated, that only now has a 25 mil waterway. This impacts on your system's performance, the fuel being consumed, because obviously the energy source has got to use more energy to achieve system to design parameter. In closed loop heating systems, the chemical reactions can lead to corrosion. And in once through water systems, we can get lime scale, which becomes a major problem. So consequences are, main things is reduced efficiency, as it says there on the screen, significantly increased energy costs, environmental impacts. That relates to, you could be on a scheme where you've got certain CO2 reduction requirements, CO2 targets. Any loss in performance will add to your CO2 output and emissions, which will result in those targets not being reached. Water treatment guidelines not being adhered to. In the small print of boiler warranties, you will see that a maintained water system is paramount to their warranty being valid. Obviously this isn't highlighted, it is in the small print. As I've covered, asset depreciation. Obviously the cost of water treatment against your mainstay equipment is significantly less. System downtime, buildings not being in use, closures, complete boiler failure. Certainly in the period of year we're coming up to off the autumn, coming into winter, these can cause significant problems, as you're aware, and liability for remedial replacement works and damage to reputation. Now, whether that be from a mechanical engineer design perspective, an installer, word does get about. We do work in an industry where rumour is rife. A couple of industry guidelines for you. Albeit a domestic guideline, in Part L, it highlights the fact that central heating systems need to be cleaned and flushed before installing a new boiler. A water treatment formulation should be added to control corrosion and formation of scale and sludge. Now, although that is a domestic guideline and Sentinel commercial is on the commercial side of the art business, it really should apply, although it doesn't, because all the commercial system is a larger scale domestic setup. BSRIA. Your BSRIA guidelines on closed heating and cooling systems for water treatment, pre-commissioning and sample monitoring in BG29 and BG50. There was recently an update over the last few months to BG29, which come into this year, which has made it a bit more stringent. Excuse me. So they've expanded to include precautions for thin-walled carbon steel pipes, closed loop pre-treatment options in the German guidelines, and some more emphasis on corrosion monitoring. Cleaning procedures in BG29 and water analysis should always be interpreted by suitable, qualified, knowledgeable specialists. That varies across the technology used, certainly when combating lime scale, which we'll cover later on throughout the CPD. Another industry association is ICOM. It's a group of manufacturers from boilers, water treatment experts like ourselves, controls, and they've all come together to put together this flow chart of how things should be interpreted in order to ensure your system is maintained fully in line with all other guidelines. I'll leave that up there just for a minute rather than me just read through it all. If anyone wants a copy of these guidelines, we can get them sent out. Liam, if you're Craig, if anyone does ask for these, could we make a note of it, please?
Yeah, will do.
Coming up to section 2. Is there any questions on section 1 before we move on to section 2? If we do it that way, it might be easier for everyone. No? Okay, we'll move on to section 2. Corrosion. Corrosion closed loop in closed heating systems, cost of poor water treatment and case studies. We're going to go over on this part. That's a lovely image to leave you with. Hope no one's having lunch. Corrosion is a natural process of surface wastage, which occurs when metal is exposed to reactive environments. Obviously, water is the reactive environment for most metals, which is why water treatment is such an important preventative measure. The image obviously on the outside is showing external corrosion. We're mainly focusing on the bottom image of an internal of a pipe. I'll pass on to Craig's slide now.
Yeah.
Craig, explain this slide.
This is, can you hear me?
Yep.
Right. It's awkward transferring over. This is one where normally when you're face to face in a room and doing the presentation, I've got the two bottles, one with brown, one with black, and you ask everybody which they think's the better and the worst water quality. Obviously, the clearer be the best. That's what you've got going in. But brown and black, generally everybody picks the black water. Obviously, it looks really dark. It looks nasty. What that is, in fact, is magnetite. So that's a water where there's little oxygen in there being active, whereas the brown is the more corrosive water quality. So if you're seeing brown water like that, it means there's a lot of oxygen acting in the system, and it's more likely to be causing active corrosion, and it's more of a problem than the black magnetite. That's me done on that one, Joe. This one, basically what you've got is you've got a cell that forms like a battery. So you've got an anodic site and a cathodic site. So the anodic site, if you see a pipe and you've got holes in the pipe work, that's where the anodic metal is being given off. And then when you get the lumps and bumps forming on the pipe work, that's on the cathodic site. But all that debris that's forming up has been released, and it's come away from the pipework or valves or other associated equipment within. So you can tell quite quickly if you're pitting or where your anodic areas are and where your cathodic areas are. It's a really simple way of looking at it, but you get lots of buildup of debris, and that's all debris that's been released from other parts of the metal in the system. Back to you, Joe.
Okay. As you can see here, different metals in contact in the heating system create a corrosion cell, as Craig said. Corrosion will take place. According to the table on the left, titled electrochemical table, one metal will corrode preferentially to another, and it's determined by the metal's position on this table. The greater the distance between the two metals is the greater the driving force between the two. Sorry, the greater the driving force of corrosion between the two metals. Depending on the component that it's made of, that's what will be left into the system. If you, for the point of this, if you make a note of where zinc is, we have a little running joke at Sentinel. Obviously, if every system could be made of gold, then we wouldn't have any issues, but we don't need to highlight the issues on that happening, unless we've got anyone in here from the Emirates, which I imagine that wouldn't be a problem. Again, relating to what Craig said about the corrosion cell, mild steel and anion can corrode in untreated and poorly treated systems. It will often result in small flakes of rust entering the stream, which can lead to erosion, sludge, bake-on deposits. Pump shaft seals as well. This can cause problems certainly with the flakes. Oxide is approximately 5 times heavier than system water. So if you say sludge, which leads to blockages, as it says there, you've got the image on the top right. The one we're probably more common with in the domestic setting would be a cold spot in a radiator, where it's got to work harder to get sufficient heat out. That will also result in reduced outputs. That's just an infrared camera showing the sludge build-up where the waterway's got to push over that. Again, some more lovely images for you. So the top image is a load of baked-on deposits onto the internals of a pipe. And the bottom image is, if you refer back to the jars of water that Craig says that we would normally show you in a physical setting, coming out of that radiator is the black oxide water. Aluminium corrosion. Aluminium is an ideal choice for heat exchangers, but it's a very malleable metal. It's obviously got high thermal conductivity, making it a great choice for heat exchangers. It has its own protective oxide layer, which is pH dependent. Is everyone aware of how pH can affect different metal environments? Is there any show of hands for that, Craig? It's just a point I normally make. Craig?
Sorry, I am unmuted. No, sorry, carry on.
So is there any hands?
No.
No. So disruptions of these can base exchange soften water, can lead to higher system pH, insufficient flushing of alkaline cleaners, and various different inhibitors elevate pH values to suit different metals. And again, that's covered a bit more further on. Stainless steel corrosion. Oxide layers on pure iron or mild steel is porous. Alloying with chromium at 11% is highly tenacious and corrosion resistant. However, stainless steel is vulnerable to localized or pitting corrosion due to aggressive constituents such as chloride and sulfate. This graph here is a new one that we've recently added, which you refer back to what I mentioned a couple of slides ago about pH environments. So if you take this, I can't pinpoint on there. So you've got the grey block down the middle of the graph between 6.5 and 8.5 pH. That is generally what's referred to as the neutral zone. That's the habitat in which all metals can cope. Now, different excuse me, different inhibitors, as we said, provide different pH buffer ranges. So you'll have some chemicals that can cope very well with copper, for example, but not so great with aluminium. So what we need to find is a neutral zone in all systems and a suitable inhibitor that can cope with all metals in the system, because it is how many different metals projects you're all working on now. How many different metal materials have you got in those systems? Craig?
Yeah. Do you want me to control it as well?
Yeah, go.
Yeah, I've got it. Obviously, then it's what's the cost of poor water treatment or no water treatment? Believe it or not, sometimes poor water treatment can be more costly than. Sorry, get my thoughts straight. Cost of poor water treatment. poor water treatment can be worse than no water treatment. So if you don't put enough in, it'll be protecting a certain part of the system, but water's got X amount of corrosive power, and if part of the system's not protected, all the corrosive power in the water will be attacking a small section of the pipework. It's not letting me flip through, Joe. Sorry about that. So on this, basically, a 70 kilowatt boiler installed with material and cost, estimated about £3,500. If you're going to clean the system efficiently with a quality cleaner and put the right type of inhibitor in, one that's specified by the OEM, so it falls in line with their warranties, you're looking at about £300 for the cleaner and the inhibitor. So it's a small price to pay. Sorry, on that as well, the right sort of the right inhibitors will last a number of years. So if you've got a nice tight system, and that's something where we say it shouldn't be losing less than 5% of total volume a year, that the inhibitor should be able to last in there for 6, 7, 8 years, as long as it is a tight system and you're not topping that system up. There are other downsides of build-up of scale and sludge in a system. The big ones being additional gas costs, obviously, and then an increase in your CO2 outputs. Our part of the solution is adding the right chemicals. We have different cleaners for different types of systems. So new systems, you're looking at getting rid of any installation. So when the pipes are being stored, the merchants, they've got a grease on there to protect, oil on there to protect them. Pumps, shafts and such like have greases in there. You need to remove all that sort of stuff. So we have something called X300, which is designed to lift mineral oil swarfs, anything on installation debris, all that side of it. When you move over to an existing system, there's a couple of cleaners, depending if you want to do a deep clean or a quick clean. So 24 to 36 hours, we'd recommend our X800. And then on the a longer deep clean, which we've done, I know Lorraine that's on here, we did one for your old firm, which were a deep clean with X4, and that did it over a number of weeks and got really good results. That's looking at removing the magnetite, corrosion, limescale, slimes, any biofouling, so lifting it out of the surface and removing it when you flush. Good tip for flushing is measure the TDS of the incoming main, and then to ensure you flushed all the cleaner out, get within 10% of the total dissolved solids of the mains water. So if you're within that, you know you've got 99% of the cleaner out of the system. Ours is it's a multi-complex blend. It's not just doing one thing. There's 9, 10 different chemicals in there that are all doing and working together to protect the system. So that, like Jay said, you're looking after different metals. So we have different things to look after: copper, aluminium and steel, and then you've got to buffer the pH, so there's multiple things for that. And then the good thing with our X100 is looking after limescale control. It is a real benefit of that system that it can look after limescale in a really good way. If you don't know the system volume, what we generally recommend is, if you're doing a new design, put a water meter onto your makeup line, and when you do the first fill, actually record out what it took to fill the system, record that, and then that gives you a good base point for putting the dosing chemicals in throughout the life of the building. If you don't know, and when we get to a lot of sites, we have to estimate. So if it's a 500 kilowatt boiler, we times that by 12 litres, which would give us 6,000 litres, where X100 is dosed at 1%. So then we'd end up with 60 litres of chemical to treat the system correctly. How do you know you've treated the system correctly? We recommend system check. So this is a sample. You get a sample of the mains water and a sample of the system water. When you're taking the sample, always let the water run out of the valve, the test point on the return, a little, so you get about a litre out, just so that there's any debris in the bottom of that valve, it's flushed out before you take your sample. Then get your sample, fill the foam in, send it off, and you actually get a lab report back, which will tell you, yep, you've done everything right, everything's within balance, and there's a nice document that you can give into your O&Ms, pass over to your client and say, we've done our part right. Yeah, firstly, obviously, if it's an existing system, check the water, plan cleaning if it's needed, select quality products. As the manufacturer of a quality product, we're always going to say that one. Confirm with the manufacturer, we're always happy, we're there to help. There's 4 of us on the commercial side that can come out, visit you and help you correctly identify what you need on each job. Add your water treatment and then test and monitor it going forward. Over to you again, Joe.
Case study. I'm trying to remember where this is to give this a bit of integrity. This was before my time with Sentinel and Craig and
sorry, I should have carried on at that point. My fault, Joe. Sorry about that. Yeah, basically it's a high skill and a new boiler system was put in the autumn, and it was run, and by springtime, the pictures on the right hand side can be seen. The aluminium had corroded, and my old boss was asked, it became legal. So my old boss was asked to go in and be a witness at the court case between all parties, and we had to give our thoughts on it. So you can go on to the next one. What we found is that the pH was up at 9.6, over 20 ppm of aluminium. Just to put that into context, you shouldn't be more than 1 ppm of aluminium, and it shouldn't be more than 1 ppm of copper, and that's why that's in red. So the copper was just over, the aluminium was 20 times where it should have been. Iron, very little iron corrosion. If you're using X100, we can look after iron levels up to 125 ppm, as long as the Sentinel X100 is dosed correctly. Something had been added to the system, as you can see by the conductivity that was raised. When the deposit water was dried out and deposit analysis done, there were 31% of it was aluminium. So the nice new heat exchangers that were in the autumn time had slowly dissolved and started floating around the system. What's happened then is the aluminium's laid onto the copper, and going back to the corrosion cell, they're disparate metals, so they start reacting together. So that's why you've got copper corrosion, and it's all to do with the pH being out on the aluminium. Yeah.
Cause that massive, great big hole.
Yeah.
Sorry, that's why I moved the slide back.
Oh, wrong. Next slide. So one of the things that we had to do was identify what had happened with the chemicals that they put in. So the idea was to push the pH to round about the 8.5 and compare it with X100. And what we found was that the brand that they'd used was very poor at buffering the pH, controlling the pH. So what we add is an alkaline solution to the made-up solution. So you make you mix the inhibitor with water to the correct standard, what the manufacturer says, and then you try and push the pH up to the 8.5. As you can see, it only took 0.6 milliliters to push it up to 8.44. With X100, it was over 8. It were up to 8 to push it up to 8.54. Slightly different, 8.44 to 8.54, but you can see there's a massive amount of alkaline solution that could be added to the X100 before it pushed it up to that 8.5. Yeah. Right, you can take it again, Joe.
Now it's me.
Yeah.
Is there
Sorry.
any questions on that at the time? Any hands up on that? I can't see them, Craig.
No.
Right. Lime scale. So what is lime scale? Mains water contains, as it says there, varying levels of calcium salts. Participation of calcium carbonate occurs approximately 35 to 40 degrees C. Progressively worsens as temperature rises. Carbonates are deposited as off-white solids on the inside surfaces, pipes and heat exchangers. More commonly, you'll see it in bottoms of kettles, domestic kettles, to give you some sort of visualization of what you're looking for. And if you didn't know, 60% of the UK is covered by, sorry, not the UK, of England is covered by hard water. Ranging, that's not the best map. I'm not a massive fan of this map because it's, unless you've got 20/20 vision, which I don't think I have, it's not the greatest. But as you see, where Craig's region is up in the northeast and west.
I'm a bit further south than that.
Oh yeah.
Yeah.
See, there you go. Well, Scotland's got no issues, but only with the football at the minute. So a lot of the southern UK is hard to very hard water. A lot of clients will stipulate that you should have something in place for, I think it's 200 ppm they generally specify, but back to the guidelines, they will always say it's over 101. Sorry, Craig, you were going to say something?
Yeah, we've got a lot of customers that start the specification at 100 ppm and above of calcium carbonate, so that's CaCO3.
Yeah.
So they start that at that level. Even in my area, it's about 137 ppm, and on a domestic system, I get lime scale. So on a commercial system where you're using a lot more water, you're going to get lime scale coming out of solution.
We mentioned earlier Part L. Part L also references there's the 200 ppm, and as Craig has said, it does vary to client, to different regions of the country, but generally anything above 100 ppm, we find that people are wanting to put measures in place, mainly down to the assets cost and replacement costs. As we said, as we touched on, the preventive treatment of this is a lot less than putting it right. I know with Adrian Flaherty, who I said hello to earlier, is a public health engineer, and Adrian's, I believe, has encountered some of these issues from time to time. So fuel wastage versus scale. There's many of these graphs flying around. I mean, to put it into context, 1.5 mil of scale will increase your energy consumption by 15%. Is that someone else coughing? So how does scale form in heating systems? Scale deposits, as it says there, can form from the initial firing of any system. High heat flux and low water volumes exaggerate the participation of calcium, and you've got, I mean, the image is there, obviously to the extreme. That's a mud flap or an inspection hole on a calorifier. Yeah, that one.
The one thing to note as well is, even if it's a top firing water heater, the lime scale still will be forming, but then it falls down to the bottom as it shows in there. And so it might not stop the water heater from working, but you're building up a level of lime scale at the bottom. What's going to happen then is it's a really good insulator, is lime scale. So it's going to stop that water in that area heating up to the 60 degrees, 65 degrees, and then you could get a Legionella problem down at the bottom of the cylinder.
More cases. Again, we've covered asset depreciation and impaired operation, and all these are prevalent with scale formations and systems. You get kettling noises. As I mentioned earlier, in the domestic setting, obviously, a lot of us are going to be used to seeing scale in domestic kitchen kettles, and that bottom image there is generally what the image we're referring to, or probably what we're all familiar with. I mean, based on that, you've got everything in the system having to work harder. As Craig said, it's a great insulator, but not the sort of insulator that we need. In hospitality settings, you will get images like this. Again, that's the top left image there is an inspection of mud flap again, where it's, as Craig said, it's compounded at the bottom. To the right is a very magnified shower head. Left is wall tiles that's got some limescale, some calcium residue, and then obviously you've got the shower valve there where you've got it on the joint where it will form.
Sorry, Jay. One of the big costs for a lot of the clients' hotels, restaurants, and such like is if they don't have hot water in hotels, they've got to give money back to clients the next morning if they can't get a hot shower. So a lot of the clients we deal with direct, there's a cost implication on their business if they're without hot water. Somewhere like a food restaurant, a quick food restaurant, if they don't have hot water for 3 hours, they've got to close for hygiene reasons. So it's not just the cost of replacing stuff, it's the downtime and what added cost that can add onto the business, especially if it has to give money back or it has to close. Over to you, Joe.
That's right. So mate, jump in whenever you want. Treating large scale and secondary hot water systems. For those of you that aren't familiar with our Sentinel commercial physical product, that's the Sentinel CalGuard there. You've got the silver anode, the water meter, our filter, and our control unit. Other types of devices on the market to combat limescale, you've got temporary solutions, which are magnetic high frequency impulse field products. I'm not going to mention any product names, but if you want to take yourself off mute and buzz in and say something, feel free. So you've got the magnetic devices, which is well known in the industry. We'll stress that these are temporary solutions, and it's temporary in the fact that they only provide a temporary change. As it says there, it's a temporary change through ionization. So as soon as water's directions change, it's affected. It's affected by booster sets. The one thing that isn't that well known is that when you're going to put a magnetic device in or a high frequency impulse field, they require what's called an LSI water chemistry test, which is a Langelier saturation index test. And it is in these products paperwork, and this isn't for our own admission, it's in their own operating manuals that these tests should be done before they're specified, Craig, or installed? Correct me if I'm wrong.
Yeah, basically it's when you're doing design, you should check what the water chemistry is. A couple of manufacturers actually do a water analysis and then compare it to the long-term average on the site as well. So from the postcode, they'll find out who the water supplier is, Severn Trent, Thames, whoever, and they'll look at the long-term average, and then they'll look at the actual result that they took from the water quality test.
So, Langelier saturation index, as Craig says, and as we've mentioned, for these magnetic devices and high frequency temporary devices. Sorry, not temporary devices, temporary methods. This is what they look for on a test. So the blue line on the graph on the blue upward line is when the LSI test was done. As Craig mentioned, they take a long-term average, which is depicted by the browny orange upward line, and your positive scaling, the horizontal line right across the middle. Earlier on, we mentioned that calcium does form at 35 to 40. We've allowed it up to 45 here. So from this, what you can see is, in order for a magnetic or high frequency device to be active and providing preventative treatment, the system already needs to be at 35 degrees for this to work. But we know that calcite starts forming at much lower temperatures. Do you want to add anything in there, Craig?
Yeah, but again, it depends what your water chemistry is. You got what supersaturated. So what you're looking at is your pH, alkalinities. It says on the left-hand side, calcium concentration, TDS, and then you plot a graph like has been done there to show the point at which it becomes scale forming. So what it's saying on this system is that if you put a unit or a magnet or electromagnetic device, wires that you wrap round, you put them on the income main, they're going to have no effect because they can't treat this chemistry of water. So what it's going to have to be is on the hot water return to the system. So you're not going to catch all the water every time. When you're on high demand, all the water's not going to be going back through the return. Some of it's going to be going in through the heater and then straight out to service when you've got high demand. So hotels, first thing in the morning when everybody's taking a shower at the same time, you could have a situation where a lot of the water hasn't actually gone through the unit because it's only on the return.
Yeah. Another thing worth mentioning with these devices.
Just the thing to say is, this is something that we don't have a concern about, because the way that electrolytic devices are working, we don't have to take Langelier into consideration. It will work from 100 ppm all the way through, no matter what the temperature of the water is. Sorry, Jay, carry on.
That's right. Sorry, let me just go back a slide. So with these devices, you'll often see, certainly, I mean, high frequency impulse fields aren't really that popular anymore, just because technology's, I think, advanced and surpassed them. Magnetic devices, if they are included in the design, you'll generally get more than one. They are so dependent because they can be affected by turbulence, as we said, directional changes in the water. So all that has to be taken into account. And it is a temporary change. So if you fit one pre-tank, you've got a 24 to 48 hour window. And again, this is in their own paperwork where this change is active. So if there's no 48 hours surpasses, that change has been undone. So in examples of where it's a commercial office building, there's no occupation over the weekend, all the water, that temporary change is going to be back to normal. It's just something to bear in mind, which is why you'll see one or two devices in place, so they can hit the system at different points. As touched on, Craig said,
sorry, Jay, just on that slide as well, it mentions high efficiency water heaters, so the new condensing type water heaters. A lot of them devices, you have to ask the manufacturer if they can cope with treating the high efficiency water heaters. It's always that conversation to have. Again, we can work with high efficiency condensing type water heaters without any concerns. Sorry, Joe.
That's right. So we move on to permanent solutions to combat limescale. Salt-based softeners is the only thing that will completely remove scale, and it will change it obviously from hard water to soft water. If you were mine and Craig's colleague Russ Wallace on the south coast, he will refer to this as, if your clients want a soft slavery shower experience. Obviously the water feels silky, it feels quite oily on your hands, but it is the only method to completely eradicate it.
But
go on.
Yeah, sorry.
Go on.
What you're actually doing with this
is like Chuckle Brothers.
Yeah, it is a bit to me, to you. Right. So what you're doing is with the salt-base exchanger, you're taking the calcium, magnesium salts out of the water and you're replacing them with sodium. So you've got to be careful that you're treating basically only the hot water services, or if you do intend to use it for drinking water, there's health and safety requirements that you know what your hardness is, how much you're removing, how much sodium you're adding back into the water, and then you've got to blend it back to a point where it becomes potable again. The other thing with softeners is there's a downtime when they regenerate, so there's a wastewater aspect to them. They do waste a lot of water every time they go into regeneration, depending on the size of the unit. Unless you blend it back, it's not classed as potable. The other one is it's actually on the HSE list of risk factors for Legionella. So if the resin bed isn't cleaned out or doesn't get a good enough flow and low flow, it can become a bacteria trap. So it is listed as a risk factor under the Legionella HSE document.
So moving on to Sentinel CalGuard, it's RAS approved. Water is potable. The technology is recommended in Part L, as we did touch on very briefly at the start of this section. It does refer to electrolytic and salt-based softeners being approved. I will make a point of note that magnetic devices and HF devices are not approved by Part M or mentioned in Part L. There's no wastewater. It's minimal maintenance. And as Craig said, it's permanent treatment, non-acids dependent, and in a maintained system, our anodes will last 10 years plus. And these are sized either by line size, by peak flow demands, and we would always suggest, well, not always, in most cases, we would suggest that these are placed pre-tank because it is a permanent change. So how it works is CalGuard delivers a low level of zinc via zinc anode and copper cathode. If you remember earlier, probably going way back now, to the metals table about where zinc was in relation to copper. They were quite far apart. All the silent. What zinc does, it holds most of the calcium carbonate in solution, and it changes it from a, so I'm lost my train of thought here. It changes it from calcite into aragonite, and the way I always refer to this is, if you think of Lego bricks or stickle bricks that obviously just stick together, accumulate to the sides of pipe, inside of pipes, other bits of equipment, that scale. By changing it, by adding zinc and changing it to aragonite, it makes it into soft flake-like structure, so it can't stick to anything. It's no longer sitting on top of each other. It is that fragile. It will wash away in the water flow. And as we said there, the image is there. That's your first image there. Calcite is that's your natural form. By then applying zinc, it then goes into this aragonite, as I said. So if you think of it as building blocks, Lego blocks, if you're old enough to remember stickle bricks, then going into aragonite. So again, more suggested actions. You need to protect against debris, assess the current system, treat every building, and specify an electrolytic, or we should say, for fairness, a salt-based system. Craig?
Yep, cheers. I can't control it, so you'll have to keep clicking.
Yeah, go.
Yeah. So obviously, some of the things that we'd recommend, As I said, it's not so prevalent now, but we did go through a period a number of years ago where it was unbarriered plastic pipe, especially on underfloor heating. That's been eradicated now, but we've got a lot of old care homes and a lot of schools where it's got unbarriered pipe and it's sucking oxygen in. Oxygen's going to kill a system quicker than anything else. Other areas are making sure pump flanges are tight. We do get a lot of pumps sucking air in. Make sure you're using a quality product. Best bit of advice, if you're not going to specify one particular thing or just make sure it complies with the boiler manufacturer's warranties. That's your best get out, and then they've got no comeback if you do have a complaint. Make sure that what you're using for treatment on your closed heating systems is covered by the boiler manufacturer. It'll protect you more than anything. Ideally, put a water meter on your fill lines. That's going to protect against, they're going to give you information you need to know how big the system is. Once you've recorded that, you can then always make sure that you're dosing the systems to the right level. From CalGuard point of view, it's always the same thing. On the incoming main, don't matter what your water chemistry is, we can protect no matter what the water chemistry, and we can also protect no matter what the water heater type is. So even if it's high efficiency, we can protect it. Going back to closed heating, check your systems, get the system check. Other ones are available, obviously, but get the system check and get the report back, and then you've got peace of mind that the water treatment has been done correctly.